this very nice conference. The title of my talk is Superconductivity, Superconductivity in spin-orbit assisted altermagnets. And okay, so I want to thank my collaborators and Herman Freire from Federal University of Goiás, Rafael Fernandes from University of Illinois, and Rodrigo Pereira from International Institute of Physics. And today I'm gonna talk about two results, about the results of these two papers published last year in Physical Review B. The main results comes from this paper here. And today we learned a lot about altermagnetism, but first of all, collinear magnetic order comes into two different setups. Mainly, until recently, we knew just, for example, magnetic systems has ferromagnetic order, in which case the Zimi splitting of the bands is complete. And of course, there is a net magnetic, there is a magnetization, finite magnetization. And we also have antiferromagnetism, in which case there is the bands are completely degenerate. There is no Zimi splitting of the bands. And here there is a little difference, because in that case, in the case of antiferromagnetism, if you change the orientation of the magnetic moments, we can recover the system by means of translation. And here, in the case of ferromagnetism, if you exchange the orientation of the magnetic moments, there is no such a symmetry. There is no symmetry that can undo time reversal symmetry. But we also have altermagnetism, in which case we can combine the properties of the ferromagnets and antiferromagnets. For example, we can have this anomalous Zimi splitting of the bands, and we also have zero magnetization. So it is possible to obtain this kind of collinear magnetic order. And the point is the following. Consider, for example, magnetic moments in the Lip's lattice, in which case we have this blue and red side describe different orientation of the magnetic moments. And if we apply time reversal symmetry, then we exchange the blue and the red sides, corresponding to the exchange of the magnetic moments. So to recover the system for the previous orientation, the previous cartoon, we can apply not a translation in the case of antiferromagnetism, but a rotation, a pi/2 rotation. And then we have the same system. And this is what we mean, I mean by altermagnetism. This is what is called altermagnetism. So if we can have a look at superconducting and magnetic states. And in the case of food ferro-Lasher-Ovishnikov superconductor, we can say that this superconducting state is the partner of this spiral magnet. And in the case of a S-wave superconductor, in which we have a finite, a constant superconductivity gap, we can say that a simple ferromagnet is the partner of this superconducting state. And for the D-wave superconductor, for a long time, nobody knew what would be the magnetic partner. And so the simplest case of altermagnetic states, which can be viewed as a D-wave ferromagnet, is this partner for this D-wave superconductor. Which means that, for example, in the D-wave superconductor, we have a gap which has nodes, and is the same for this altermagnet. So altermagnet, as I said, the simplest case of altermagnet is the corresponding partner for D-wave superconductor. And how about the may compose the compounds which are candidate to altermagnets. We have metals. We have metal with vial points. We have semiconductor, and we also have insulators. So there is a zoo of candidate materials for altermagnets. And besides that, how do we describe and what is the order parameter for altermagnet? If we focus on the case of a system that there is no spin-off interaction, for example, we can describe altermagnetism, the local magnetization, by this kind of function. And so it is we have a constant vector, and we have a function which depends on the orientation of basically on the angle orientation. We can have a dependence of some kind of phase. But let's forget about this phase, and for example, let's say that we don't have a phase, or Q equals 0 phase. And for this kind of order parameter describe altermagnetism, this form factor has to transform in this way under crystalline symmetry, for example, under rotation. Because if you apply time reversal symmetry, then you have to exchange m naught by minus m naught, and for the system has a zero magnetization, then we have this form factor must have this kind of properties. And this is for the case where we don't have spin-off coupling. And how about if we consider some kind of spin-off coupling? What happened to the order parameter? And the result is the following. The form factor must have dependence, which means that the components of the magnetization are not actually, each component of the magnetization must acquire a difference depends on angular dependence, which is different from that case in which the situation we describe all components of the magnetization has the same angular dependence, and if we consider the spin-off coupling, then the situation changes. But at the same time, this form factor, this vector form factor must transform as an odd function of this symmetry operation. So this is the main consequence of spin-off coupling when we have an altermagnet. So, and how about the electronic properties? To describe the electronic properties, we can start from this kind of Hamiltonian, and the electronic quasi spin we couple to the form factor of describing altermagnetism in this way. So we have a phi, which is the altermagnetic order parameter for this electronic model, and the main question is to determine the properties of the form factor. And of course, we have a non-interacting Hamiltonian, and we have this interacting Hamiltonian, and as I said, it is possible to obtain for each point group the dependence of this form factor. And I'm not going to talk about how to obtain this, but I'm just focused on the results. For example, if we consider the tetragonal system, in which case the order parameter, the phi, transforms as a one-dimensional reducible representation described in this column. And for example, the B1G reducible representation of the tetragonal group, in which case the minus sign is just to represent the break of time reversal symmetry of the altermagnetic state. And we start describing the properties of the electronic bands. And in order to do that, we first look at the zeros of the form factor. The form factors is zero along some lines. And in that case, for the tetragonal system with the B1G order parameter, you have 3 lines. And at each line, the we can look at the diagonal. First of all, we have to diagonalize the Hamiltonian, and when this form factor is 0, then we have degeneracy, the bands for the plus spin up and spin down become degenerate. And most of all, most important, we have this kind of the degeneration means that when this electronic band is 0, is the time the Fresnel phase, then the Fresnel phase becomes degenerate at some points. And these points describes something very important, namely type 2 Weyl nodes. And the type 2 Weyl nodes is the main feature is this tilted cone, which appears in that case. And so we have a set, in this case, with 8 Weyl nodes, 8 type Weyl nodes. And we can confirm that this is the case by expanding the Hamiltonian, this altermagnetic Hamiltonian at the Weyl points, and we obtain the characteristic form which describes this kind of nodal points for any electronic system. And how about the protection of the type 2 Weyl nodes? And besides, how about the protection of these how can I say, of the nodal lines? The question is the following: are the nodal lines protected? And the answer is yes, at least in the following way, because the nodal lines do not have topological protection because they belong to this class C, and this class C means that they are not protected by but how can I say? They are not they are not topologically protected, but they are protected by these by crystalline symmetries, which means that if we apply some kind of perturbation that does not break for example, the mirror plane symmetry of this group that describes the altermagnetic system, this means that there is we cannot get out these nodal lines. And for example, let's say that we apply a magnetic field. If you apply a magnetic field in an altermagnetic system, we have just to include the Zeeman interaction in the previous Hamiltonian, and if this magnetic field does break the mirror symmetries of the point groups, then we can say that the nodal lines are protected. We cannot get out the nodal lines immediately. So, for example, let's say that I apply a magnetic field in the Z along the ZX, and we look at the mirror planes, which is the XY planes. In the absence of the magnetic field, we have these nodal lines, which are straight lines. Then, if you apply this, if you increase the magnetic field, then the nodal lines become nodal loops. And so here we have we have degenerate electronic bands, and if we increase even more the magnetic fields, then the nodal loops becomes points. And if we exchange the direction of the magnetic field, then the nodal points change the direction. So we have a break, and the system has a break of tetragonal symmetry, which means we have, in this case, autonomic system. If we change the direction of the magnetic fields, then the nodal points will appear along this in the other diagonal. And we can look at the type 2 Weyl nodes, and if we increase the magnetic field, then the Vanuildo nodes, which are located along these mirror planes, which are perpendicular to the magnetic fields, start to change the position, and at some point, these nodal Vanuildo nodes will collapse, and then after the collapse, we can have the separation, the full separation between the firm surface in that situation. Okay, and we can describe this transition with the application of the magnetic field by looking at the area of the nodal loops. And at the same time, we can look at the gap, the Zimi splitting of the bands. And for example, if you apply a magnetic field along a perpendicular to a mirror plane, then the area of the nodal loops start to decrease, and at some point, for a critical magnetic field, they collapse in 2 points, and after that, the Zimi splitting will be complete, and there will be a finite gap between the bands. And so we can say that when we have a finite gap between the bands, we have a ferromagnetic state, and otherwise we have an altermagnetic state. And this is a transition, some sort of topological transition between an altermagnet and a ferromagnet. On the other hand, if you apply a magnetic field along a direction, in which case there is this field is not perpendicular to any kind of mirror planes of the point group, the tetragonal point group, and we'll have from the beginning, even for infinitesimal magnetic field, a finite gap in the band structure. So it's trivial. But we can have a topological transition, depends on the direction of the magnetic field. So altermagnetism is connected to several phenomena in condensed matter. And how about the impact of for example, the nodal lines on something very fancy like superconductivity? And this is the question that I want to answer. What is the impact of altermagnetism on superconductivity? Since altermagnetism has the properties, for example, of ferromagnets and antiferromagnets, it is not possible to know from the outset whether altermagnetism will favor spin singlet superconductivity or spin triplet superconductivity. Then this question can be answered in this form, in which case we consider, first of all, this Hamiltonian. The first Hamiltonian describes an altermagnetic system, and we have a spin-off coupling, which means that the form factor is a vector, and we consider this kind of pair interaction, and the pair interaction will favor both singlet and triplet superconductivity. And as always, I'm going to consider a tetragonal system described by a B1D altermagnetic order, and we can look at the table, and this is the form factor. It depends on both kx, ky, kz, and this form factor has this kind of spin texture, and the spin texture on the fan surface will have this kind of continuous dependence, which is different from the two-dimensional case without spin-optic coupling. And then we can apply the BCS theory, and here we have the Bogoliubov-Dejean Hamiltonian, and this H0 is simply the altermagnetic Hamiltonian. You have this spinum, and what I'm looking is the region of the phase diagram, in which case I'm going to consider superconductivity alongside altermagnetism. So I'm assuming that the system has altermagnetic order, and then on top of the altermagnetic order, I consider the superconductivity. So this is the order parameter, the superconducting order parameter defined in terms of the expectation values. And most important, I'm going to consider, as I said, and superconducting order parameter with spin singlet superconductivity and spin triplet superconductivity, right? But let's look at the moment just to spin triplet superconductivity and spin triplet superconductivity. And for example, if I start with the spin singlet superconductivity, I can obtain this gap equation. And the gap equation for spin singlet superconductivity depends on TC_S0, which is the temperature in the absence of the spin, in the absence of the altermagnetic interaction. And it depends on this function, upsilon, which is a positive definite function when x is positive. So because of this minus sign, this equation means that if I have this kind of wave function or order parameter for the spin singlet superconductivity, which is positive because we have this function is actually this absolute value is positive, then this is positive, which will mean that if I increase this interaction, then this temperature, the temperature for the spin singlet superconductivity in the presence of altermagnetism must decay. And we can test these results for even for S-wave wave function or D-wave wave function, and the result is the following. Then we have always, if I increase this interaction, this coupling, the altermagnetic coupling, at some point the temperature, the transition temperature for the spin singlet state will go to 0. But how about the citation? If you look at the citations of this spin singlet state, we can obtain that we can find that for some of the dispersion, they have 0 solutions. The 0 solution for this dispersion means that the spin singlet state in the altermagnetic with altermagnetic order has Bogoliubov-Fermi surface. And the question is, are such surface protected by some sort of symmetry? And the answer is yes. Why? Because the system, of course, has charge conjugation symmetry, but the spin singlet state has also parity symmetry. And since the system breaks time reversal symmetry and the square or the CP symmetry is equals to 1, this Bogoliubov-Fermi surface has a topological, a Z2 topological charge. And most important, the Z2 topological charge has we can obtain the topological invariant, the form of the topological invariant in terms of the Pfaffian. Because there is a unitary transformation we can apply to the Hamiltonian and then obtain this expression. And the Pfaffian is 0 exactly at the Bogoliubov-Fermi surface, and change sign when we cross this Bogoliubov-Fermi surface. And then the expression for the Z2 topological invariant is given in terms of the Pfaffian. And how about the spin triplet case? The spin triplet case, we can derive this kind of gap equation, and then we have the minus sign, we have a positive function for the upsilon, and here the absolute value of this function is also positive, which means if we increase the altermagnetic interaction, then the transition temperature for the spin triplet case, in that case, goes to 0 at some point. And if we test these results for for some of the wave function describing this spin triplet case, we can obtain the results. But the difference is the following. The temperature doesn't go to 0 at a finite altermagnetic interaction. Instead, it goes to 0 as a power law. So it's the altermagnetic phase is not so detrimental to the spin triplet case. And how about the zero? Okay, first of all, we have to look, even though we have this minus sign, if you look at this dependence of this gap function, okay, the temperature cannot go up, but at least if we have a 0, which means since we have a dot product, and if the gap function for the spin triplet case is given in terms of this cross product between a function u and the altermagnetic form factor, then the right-hand side of this equation is 0, and then the temperature to the spin triplet case is constant. Which means that because of the Fermi-Dirac statistic, the u function must be an odd function of momentum, which means, for example, in the simplest case, this function has p-wave symmetry, and the form factor for the altermagnetic phase has, for example, d-wave symmetry or g-wave symmetry, and if we combine these two symmetry with the symmetry of the u and the g, we arrive at the symmetry of the spin triplet case. So the spin triplet superconductivity is described by F-wave symmetry or H-wave symmetry. The F-wave symmetry is when we combine the P-wave symmetry of the U function with the D-wave symmetry of the altermagnetic form factor. So there is an infinite set of spin triplet pairing states which are not suppressed by altermagnetism, which is contrast with the result for spin singlet superconductivity. And how about the excitations? How about the excitation of the spin triplet states? There is, because the spin triplet case breaks the parity symmetry, it is not possible to have a Bogoliubov-Fermi surface. Instead, the spin triplet case has Weil pinch nodes, which means that the Fermi surface of the altermagnetic normal state will get out along everywhere except at the Weil pinch points. And the Weil pinch points will be along the nodal lines of the normal states altermagnetic phase. So the Weil pinch points will be along this nodal line defined by the zeros of the Fermi factor and the nodal lines of this cross product between the U function and the form factor. But anyway, we can evaluate, for example, the Berry phase of these nodal lines, and of course the Weil pinch point, and show that they have a non-trivial Berry phase. And here we have an example. We consider this F-wave gap function for the spin triplet case, and we have here the Berry connection. And if we calculate the Berry phase along the the nodal line along the ZX, we can show that they have a non-trivial Berry phase. So the spin triplet case is a topological phase in the sense that it has a non-trivial Berry phase. And how about coexistence? We can look at the coexistence by evaluating this free energy, this Ginzburg-Landau free energy, up to fourth order. And here we consider this dependence for the spin singlet, spin triplet phase, and we have amplitude, and we have the phase between these two states, and theta is the phase difference between the order parameter. And so, since this gamma 2 parameter of the Ginzburg-Landau free energy, since it is finite and positive, this means that if we have finite amplitudes in this Ginzburg-Landau free energy, then because of the sign of the gamma 2, this implies that the if you have a coexistence, then between the spin singlet and spin triplet case, then the coexisting phase will break time reversal symmetry. And to prove that, we minimize the free energy for the spin singlet spin triplet case. And for example, if I consider S-wave superconductivity and F-wave superconductivity, spin singlet spin triplet case, there is no coexistence because the Ginzburg-Landau free energy breaks down. But on the other hand, if we consider D-wave spin singlet D-wave state with F-wave triplet state, then there is coexistence, and this is illustrated by this in this figuring, where we have F-wave and D-wave F-wave order parameter. And here, just to show that the gamma 2 is positive. Okay, since I'm out of time, I'm going to leave here the conclusion of my work. Okay, thank you.
Thank you. We have time for questions.
Thanks for the presentation. I am thinking about in the possibilities of the altermagnets when reach the superconductor phase, if this can be drive possible theoretical approach to the topological superconductor. So if this has some stability, like if they are, how can I say, if these phases, these two phases are stable.
Yes, for example, if I consider, let's start from let's consider the spin singlet state. The superconductor is stable in the sense that if you apply some kind of perturbation that doesn't break this, doesn't break the CP symmetry, then it is stable. But the interaction that you apply to the superconductor must preserve the CP symmetry. In that sense, yes. How about the spin triplet case? The answer is the following. If you apply perturbation that preserve the mirror symmetries of the normal altermagnetic state, then yes, you have stability. For example, if I apply a magnetic field that is perpendicular to a mirror plane of the normal altermagnetic states, yes, the spin triplet case is stable in that sense. But you have to preserve some of the symmetries of the altermagnetic states. Or in the case of the spin singlet state, you have to apply a perturbation that doesn't break the CP symmetry.
Okay, thanks.
All right.
Other questions?
Vanuildo, this equation here, when I look at that, right, it looks like you have kind of the altermagnet is acting as an impurity, like an average impurity, right? Because the upsilon function is just because of Gorkov, right?
Yep.
So I remember that there were cases, and you showed two cases. Singlet, it goes to 0. Triplet, it doesn't really go to 0 unless lambda is infinity, which is not the case, right? So it reminds me of cases of impurities where you start with a state, and then you start increasing the disorder, there's a phase transition to another state. So could it be that if I solve self-consistently, maybe that's what you did. I start with S wave, and then I start increasing lambda, I have a transition to majoritarily P wave at higher lambda? I'm just thinking of the S++ to S+ transition driven by impurity. That sounds very similar.
I think it is possible because Yes, there is some, how can I say? I didn't solve the for both states because of because of the complexity of the gap function. And the answer, it is possible, but I have to do the calculation. And of course, we can have, I made some approximation. For example, I consider the density of states is constant for along the whole Fermi surface to obtain that result, which means that if I consider just a full calculation, it is possible to have coexistence between both states, singlet and triplet states. But I tried to simplify the results just to obtain something which is how can I say, something the most simplest solution for the problem.
Other questions? Okay, let's thanks Vanuildo again, and let's thanks all the speakers of the day.